let's look at magnetic forces on currents. So we've already seen that moving charges, also known as currents, create magnetic fields. And we've already seen also that magnetic fields will cause forces on moving charges. So if a moving charge is the same as a current, then it stands to reason that a magnetic field will cause a force on a current. So if you have a current moving through a magnetic field, the current will feel a magnetic force. Well, the question then becomes how much force and in what direction? Well, to determine how much force, let's go back to this equation. F is equal to QVB sine theta. That's the equation for the magnetic force on a moving charge. Well, I'm going to rearrange a couple of things. Let's say that the velocity, that's equal to L over T, where L is how far the charges travel, and T is how long it takes them to travel that length. Well, I can move things around a little bit. I can take the T in the denominator and move it under the Q. And if I do that, I have Q over T. Well, Q you can think of as the amount of charge that's traveling, the amount of charge that's going to feel this force, and T is the amount of time for that charge to move the length L. Well, Q over T is just current. That's all it is. And so F then is equal to ILB sine theta, or sometimes this is written as F is equal to BIL sine theta. And let's define everything there. So F is the force experienced by the current, B is the magnetic field strength, I is the current that we're concerned with, L is the length of that current that's in the magnetic field, so that's the length of the current that experiences the force, and theta is the angle between the current and the field. All right. So the next question would be, what's the direction of the force? Well, we've got a right-hand rule for that. Of course we do. And it's the same right-hand rule as for the force on a charge moving in a magnetic field. The only difference is that instead of pointing our fingers in the direction of the velocity of a charge, you point your fingers in the direction of the current. So let's do a quick example. Let's say that I have a current traveling to the left, and then I have a magnetic field that's directed into the screen. And I want to know the direction of the force on that current that's within the magnetic field. So take my right hand, I'll point my fingers in the direction of the current. So my fingers of my right hand are pointed to the left. And then I have to direct my palm so that the magnetic field is coming out of my palm. So my palm is directed so facing the screen. It's kind of directed or pushed onto the screen. If I do that, then the force is in the direction that my thumb points. And in that case, my thumb is pointing to the bottom of the screen. So the force on that current would be toward the bottom of the screen. Let's do another example. Let's say that I had a current coming out of the screen and a magnetic field directed toward the bottom of the screen. So in that case, I would take the fingers of my right hand and I'd have them pointing out of the screen directly toward my face. And then I'd have the palm oriented so that the magnetic field is coming out of the palm. So my palm is facing down toward the bottom of the screen. And if I do that, then my thumb points in the direction of the force. And I find that my thumb points to the right. So the direction of the force on that current would be to the right. All right, let's do one more example. Let's say I have two currents and they're both directed toward the bottom of the page. So maybe I have two wires, parallel wires, that are both carrying a current toward the bottom of the page. And I want to know what force will I2 experience due to I1. So let's take this step by step. I1 creates a magnetic field. That magnetic field created by I1 is what I2 will then move through. I2 will move through the magnetic field that's created by I1. And if I2 is moving through a magnetic field, then it will experience a force. So that's the background here. Let's figure out the magnetic field created by I1. Okay, let's do that. Starting place. Well, on the left side of I1, we'll use our right-hand rule to find the direction of the magnetic field created by a current. So on the on the left-hand side of I1, the field would be directed into the page. On the right side of I1, the magnetic field would be directed out of the page. So take a moment and make sure that makes sense. I have just used the very first right-hand rule that we ever learned to determine the direction of the magnetic field surrounding I1. Okay, I2 moves through that magnetic field. So now we can figure out the direction of the force on I2 caused by the magnetic field that was created by I1. Okay, and for that we're going to use the other right-hand rule. So for this right-hand rule, I point the fingers of my right hand in the direction of the current, and I2 moves toward the bottom of the page. So my fingers will point toward the bottom of the page. Then I take my palm, and my palm is going to be directed so that the magnetic field comes out of it. And the magnetic field caused by I1 at I2's location comes out of the page. So my palm is facing out of the page. And if I do that, my thumb is pointing to the left. So the force on I2 will be to the left. All right. So what ends up happening is that I2 is experiencing a force toward I1. That answers the question, but let's take it a step further. If you did the same argument, if you found the magnetic field created by I2 and then figured out the force that's acting on I1, you would find that I1 would feel a force to the right. In other words, these two currents that are both traveling parallel to each other will be attracted to each other because of the magnetic force. And you can also look at a situation where the two currents are traveling in opposite directions, or what we would call anti-parallel, where one is moving toward the bottom of the page and then one is moving toward the top of the page. If you do that, and you go through all this reasoning, what you would find is that those two currents would repel each other.